Hey, what's up, Chem peeps? Who's ready for some free response practice? I know I am. The Lewis electron dot diagrams for 3 substances are shown below. Use your knowledge of chemical bonding and molecular structure to answer the questions that follow. Pause, take a moment, look at the different structures. Part A. Describe, in terms of valence electrons, how the chemical bonds form in the substance represented in diagram 1. As we take a look at diagram 1, notice the bond is between a potassium ion and a bromide ion, a metal ion and a nonmetal ion. This first Lewis electron dot diagram is representing an ionic bond between potassium and bromine. So let's think about, in terms of valence electrons, how an ionic bond forms. A valence electron is lost by potassium to form a positive ion. Potassium's lost electron is gained by bromine to form the negative bromide ion. The resulting attraction between oppositely charged ions results in an ionic bond. Boom. Part B. Which of the samples, when dissolved in water, will create a solution that is a strong electrolyte? Explain. Alright, we have already identified diagram 1 as being an ionic compound. Diagram 2 and diagram 3 both represent covalent compounds, as the elements involved in these compounds are all nonmetals. Recall that ionic compounds, when placed in water, will dissolve into their ions or charged particles, making them excellent electrolytes. Samples from diagram 1 will create a strong electrolytic solution. Diagram 1 is an ionic compound. When ionic compounds dissolve in water, their ions are free to move about the solution and make them strong electrolytes. Boom. Part C. Are the molecular geometries for the molecules depicted in diagram 2 and diagram 3 the same? Explain. Well, as we take a look at the diagrams 2 and 3, notice that one of the shortfalls of Lewis structures is that it's difficult to get a 3-dimensional representation. So to help you out, I've got PhET Vespers simulations to the rescue. Once again, PhET coming through in the clutch. Yes! As you take a look at the Lewis structures, their geometries appear to be the same. But let's take a look at the 3-dimensional structure of these 2 molecules. Note that their electron geometries are the same. There are 4 regions of electron density about the ammonia molecule and the methane molecule, CH4. However, their molecular geometries are different. Recall that the molecular geometry is focused on the geometry that exists between only the bonded regions of electrons on that molecule. In ammonia, because one of those regions is a lone pair region, the molecular geometry here is trigonal pyramidal, whereas in methane, or CH4, all of the regions are bonded regions, and therefore the geometry here is tetrahedral. No, nay, the molecular geometries depicted in diagram 2 and diagram 3 are not the same. Diagram 2, molecular geometry is trigonal pyramid. Diagram 3, molecular geometry is tetrahedral. Boom. Now if you're thinking to yourself, well, that's great, but I'm not going to get a fancy schmancy simulation to use on the exam. It's super important that you're able to determine the molecular geometries simply by counting the regions of electron density about the central atom of the molecule, and then thinking about how many of those regions are lone pair regions versus bonded regions. Just takes practice. Plans for the weekend? Check. Part D. Would you predict the H and H bond angle in diagram 2 to be larger than, smaller than, or equal to the HCH bond angle in diagram 3? Explain. Again, here's one of the pitfalls of Lewis structures. It appears that the bond angle here is equal to the bond angle here, that they're 90 degrees. But you have to remember, these molecules exist in a 3-dimensional world. The 3rd dimension. Boop, boop. Now, as you take a look at the 2 molecules, notice that although the molecules have the same number of regions of electron density, they each have 4 regions, the bond angles are not the same. Recall that lone pair regions of electrons repel more strongly than bonded pair regions. And so note that the HNH bond angle in ammonia is slightly less than the HCH bond angle in methane. The predicted HNH bond angle in diagram 2 would be smaller than the HCH bond angle in diagram 3. While both structures have 4 regions of electron density, in diagram 2, one of those regions is a lone pair region. Lone pair regions repel more strongly than bonded pair regions, and thus decrease the bond angle. Boom! Part E. The molecule depicted in diagram 2 is highly soluble in water, whereas the molecule depicted in diagram 3 has limited solubility in water. Account for the difference in solubilities between the two compounds in terms of intermolecular forces. Intermolecular forces between molecules of diagram 2 and water include London dispersion forces, dipole-dipole, and hydrogen bonding. IMFs, intermolecular forces between molecules of diagram 3 and water include only London dispersion forces. The stronger intermolecular forces between molecules of diagram 2 and water account for its higher solubility. Boom. That brings us finally to part F. Diagram 3 represents one nitrogen atom bonded to 3 hydrogen atoms. In their respective boxes below, draw a valid Lewis structure for a molecule of NH4+ and a molecule of NH5. If a valid Lewis structure cannot be drawn, write no valid Lewis structure in the box. Alright, NH4+, definitely possible. The ammonium ion. First, let's calculate total number of pairs of valence electrons we have to work with. Boom. Don't forget, because this is a positive ion, you have to subtract the number of electrons equal to the charge in that ion, which gives us 8 total valence electrons to work with, or 4 pairs. Nitrogen is going to go central, and we're going to surround it by our 4 hydrogen atoms. Boom. Connect each of these hydrogen atoms with a pair of electrons to our central nitrogen atom that uses up all of our pairs of electrons. As I take a look at my final Lewis structure, this represents a valid Lewis structure for the ammonium ion. Nitrogen must follow the octet rule, and it has 8 electrons. Hydrogen, being an exception, only requires 2 valence electrons, and it does. To finalize the ammonium ion, I'm going to place this sucker in some brackets and put the charge outside. As I look to NH5, it's important to note that compared to NH4+, that we can't draw a legitimate Lewis structure. Nitrogen strictly follows the octet rule, and although you can have some elements that are on period 3 or below to expand their octet, nitrogen is not one of them. And if you tried to attach 5 hydrogens to our central nitrogen, that would give nitrogen 10 valence electrons, which isn't going to happen. No valid Lewis structure. Boom. And we are done.